So we are back with the error correction. We are here to learn. So let's go through these carefully, step by step. Let me see. Let's open the stuff. So workspace, we're doing, what was that? Counting, oh, QSC. And so we've got basically, that name sucks, Jupyter Notebook. I gotta change the name. Mm, so Shor's error correction code. My thought until now was that so if we want this to behave like a single qubit, we need to figure out how do you apply operations, right? And the whole point here is that I thought, so can we rename this? Sure. Okay. And so the whole point of doing these is that you encode zeros when all the three qubits measure 0, and you encode 1 when all the three qubits measure 1. And kind of everything else in between, right? So the reason you're using 3 qubits is that you're kind of it's for this error correction, because if an error happens somewhere in here, right, somewhere where the E box is, so let's say here goes your circuit, really, or your operation, and if an error happens randomly in one of those qubits, then chances that they happen all over the place are lower, right, because they have a lot of qubits. And so the circuit should be able to correct it. So, but it doesn't seem to work as expected. Let's go through these again, see what we have. And we're doing this. So we're doing these. You know. So this is the first part of the circuit. Let's check that we have everything. So circ step through, because I probably would like to step through that and use that chance to actually see if stepping through helps. That's a debugging kind of thing. Stepping through a circuit. Okay. So, so we've got these things. Seems to be correct. So, to be honest, okay, so let's take a look at what's the state after the first encoding part, right? Let's see, because this should be whatever initial state it is, just kind of 3 times repeated somehow. Let's see. So that's the encoding circuit. Should I run the whole notebook just in case? Maybe. Have I run this? Yes. What am I doing? This. The whole thing. Oh yeah, that doesn't make any sense. Cell, edit, delete cells. We've got the test circuit. Simulator and the count. Okay, so good. So how do we do this? Pen basic circuit for I, and step in enumerate simulate moment steps. So you're simulating moment by moment. That's nice. Okay. So I can actually copy these 2 lines, and that should work. We are doing this with the encoding circuit. So encoding circ, right? NP around step state vector. What does this mean? Okay, these are just a replacement of the variables. Okay, I, then this goes the, so it's a rounded version because otherwise you're gonna get too much precision, I guess, with the numbers in here. Bum, 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 bum. Where am I here? So simulator is not, it's sim. It's sim. Sim, sim, sim. Sim, sim. What's going on here? NP is not defined. No way. Where the NumPy as NP. What? Okay, because we got 9 qubits now, so that's a huge state. So it's all zeros. Then, what? That's gonna be impossible. That's gonna be impossible to debug. That's gonna be impossible to debug. Step 3. How could I? Is there a better way to step through? So I see a lot of different phases in here. How can I? Because I cannot just ignore the zeros, right? Because some of them have a negative phase, and that's important. Okay, but it's zero amplitude at the end of the day, so who cares? If I just would keep the ones that are non-zero and kind of their index, will make it easy for me to see. Oh, what is it that we have here? State vector. Can I plot the state vector somehow? Can I have the state vector somehow in a nicer... Step result, set state, state. How can I... How can I visualize this better? That doesn't... It's just a lot of stuff. State vector. So, state vector. Can I just like... Can I do something with the state vector? Block vector from state vector? Measure state vector? State vector? Sparse simulator? Wave function trial result? Validate state vector? Density matrix from state vector? That's going to be a big matrix anyway. State vector like state vector direct notation. Oh, that's nice. Okay. How can I do this? Returns the state vector as a string in direct notation. Okay. That's definitely decimals, how many decimals to include in the pretty print? State vector mixing. Can I just say, can I just print that? Can I just do this? Oh, that's so. If I just do step state vector, um, well, I think it would be nice to print this stuff. Okay, can I just now do this? It's an array. So how can I get the circ print state vector direct notation? Parse simulator step. Parse simulator step. So maybe, okay, so maybe, ah, maybe this is something I can apply, sorry, here. Yeah, nice. Okay, cool. Um, mhm. Hmm. So, how to read that? What is the coefficient of the zeros? Okay. Oh, sorry, because I should, I'm missing here your notation. So I'll just go back to what I had before. And this is basically the Dirac notation. That's much more useful. Dirac notation, what have I got wrong? Oh yeah, that this doesn't need the NP thing, the array. Stay, okay, I like it. So can I just print a line break? How do you do a line breaks in here? Yeah. So first is 0. Then we're entangled with the fourth qubit, right? And that's the first step in here. Kind of sucks that this Hadamard and this is done at the same time, because that's giving me. So how can I make sure that things get added in separate moments just for the sake of? It doesn't matter, because those it seems like those three operations kind of happen at the same time, which is fine, but it just makes it difficult to debug. What do we got at the end? That's what matters, right? So it's a combination of all zeros, or the last register 1, or the middle register 1, or all the registers here 1. Ah, interesting. How is that so, though? That's still supposed to encode all zeros, right? Because I'm doing the encoding circ. So if I print encoding circ, all zeros. And how does this change? So this is the final step. It's an entangle. Something's not. Hmm. Hmm. I'm not so sure what's the point in here, the short code. So, look. Okay, so this is a 0 and this is a 1. Okay, that's the point. So this is the way you encode a 0, and this is the way that this setup encodes a 1. So the error channel may include either B flip, percent flip. It's possible to correct lately, the quantum channel can originally corrupt a single qubit. The first 4 and second qubits are for the sign flip, with the 3 group qubits are designed for the bit flip code. With the Shor code, the qubit state transformed into the product of 9 qubits, where like a 0 string is the equivalent of. Okay, so it's encoded in the signs, so that's the difference. So we're of 9 qubits. If I change if I say so if I basically how can I do that? I forgot. Okay, I create a circuit. So initial state. So it's a circuit, right? Circuit. And now I do initial state. Is can I do that? No, I gotta append that. And basically all like if I do print initial state. So this is these, right? And then if I do if I copy the same and I do this with initial state plus, can I do it like this? If I print initial state plus encoding plus encoding circ, then initial state is not defined. Initial state. Oh yeah, okay, that works. So if I just do these and I do, I'm trying with a lot of different little things because I'm not super familiar with Python anyway. So initial state. So that's the reason. So if I do these, what do I get? Okay, so this is different now. But let me see. So design for the flip code. A qubit state will be transformed into the product of 9 qubits. If a bit flip error happens to a qubit, the syndrome analysis will be performed on each set of states. Then correct the error. If the 3-bit flip group 1, 2, 3, 4 are considered as 3 inputs, then the shortcode circuit can be reduced as a sign flip code. This means the shortcode can also repair sign flip error for a single qubit. The shortcode also can correct for an arbitrary error, both flip and sign flip on a single qubit if an error is modeled by a unitary transform. Okay, but so how does this work though? So what I'm basically seeing here is that it's not. So the output, right? The output of the circuit is not the wrong, what I was doing wrong is I just measuring this qubit, and what I should do is before measuring anything, I should just try to transform that. Like I should basically try to read the sample the actual state, and then I know whether this is a 1 or a 0. So let's do the following example. So let's assume this is correct, and let's assume that this is what happens. So this is the state that basically, this is what it means to have 1, right? So if I go and I now take test X, okay, without the measurement, right? So let me get rid of the measurement. So test X is these, with the X's all over the place. I corrected one thing. I had forgotten an X in here. So I corrected, because I did this right after the video. So there was an 8 here. This is a 9 now. So if I step through the whole circuit, at the end, I should see the same like I see here now, right? Because this is the state that encodes a 1, a logical 1, okay? So if I do the same now, but with test X, so test X starts with 0, that's a layer of X gates in the middle, and then that's what I'm expecting will happen, right? So test X. No. It's actually all zeros. What? But even from state 9. So test X. 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, maybe not. Maybe that is actually indeed 1, 2, 3, 4, 5, 6, 7, 8, 9. The step 1. So these should match these, but it doesn't at all. Okay. Maybe. So how would you? So if that encodes, okay, so this encodes zeros, this encodes ones. From thinking whether I'm like looking at it from a whether I'm looking at it in the right perspective. E phase. What if I apply again the X gates just on these 3 qubits? Because they are the ones that encode the. Yeah, that doesn't make sense either. That wouldn't make sense. Come on, let's think. Let's think about this carefully. So, we're trying to learn here something. So, flip bits are on a kind of error class, but the original state of the qubit will be changed into this state. The Harman basis flip size be a quantum channel that can cause at most one phase flip. Can cause at most one phase flip, and yeah, exactly. Because if 2 things get phased, then it will just think it's one thing. It will just correct. It will just autocorrect. So I was right in saying that you actually have to read the first qubit. That's really what you'll have. Yeah. So I was not okay. So that was not a good idea. That was definitely not a good idea. So that this encodes one. I mean, does encode one, right? The thing is how to apply a next gate in there so that I read a one at the end, right? If I want to read a one in here, those two must be kind of one, right? So if I kind of go back in here, it's kind of one. Yeah, but it's kind of. So if I if this is zero, if it's zero, so everything is kind of zero, right? So it's all encoded in here. So if I change the bit here, here, and here, this will get negated. And so if we had a I cannot paint over this. What? I cannot paint over this. So if I cannot paint over this, it sucks. Maybe I can open in a new tab. Also not. So here we're gonna get in the qubit 4 and 7. So sorry, 3 and 7, starting from 0, right? 3 and 3, 4, 6, 3 and 6. Okay, because you're getting into you're applying a Hadamard gate first. So so maybe I should apply a Z gate, because then if I apply a Z gate to these qubits, let's see if that happens. Maybe I'm just being stupid. So what if it's just a Z gate which you need to apply? That is not defined. That is not possible. So the Shor X would be apply a Z. And so now I got all Zs. If I go here, yeah, now I got a 1. Damn it. Okay. Really? So to simulate that, I have to. So the way you do operations using this code is by changing the you have to apply the axis counterparts. So if I go again, if I just now add the measurement again, right? So I've applied Z gates everywhere. I'm lost. So good. So basically, because the reason is that you've applied the Hadamards because you're mixing here also the phase correction. Like if you wouldn't do that, if you would just and so if you want to apply a next to this, if you want to measure a 1 in here, you gotta change the. So if I wanna apply, for example, let's say I want to apply a bit flip. Okay, so maybe what I should do is, yeah, I can just wrap everything into another, like into Hadamard again, right? That should work. That should save my, yeah, of course, it should save my mental effort to actually have to translate those operations. If I just do, wait. So where's where's Shor? Where's the Shor X thing here. So if I do basically a Hadamard sandwich plus the actual operation I want to do, and then another Hadamard sandwich. Okay, so I actually got to do it this way, and then I probably, so if I print these, yeah, so I get everything wrapped up by Hadamards, and now if I run these, I should get the same result. Please, 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 please. Yes, yes, yeah, perfect. I wonder how could you? Yeah, okay, so you know what I mean. Like this is a side effect of trying to do two things at once, right? Of trying to protect the phase flip and protect the bit flip. Okay, we got something. That's nice. So let's maybe clean up a little bit, and then because what I would do then in the next part is I would just kind of make an actual class called logical qubit or something like that, and then I'll try to like just have something a bit more cleaner. How do I clean that up? So basically, we've got the encoding circuit, we've got the decoding circuit, and so we just need now a way to programmatically make that is okay. So each operation you want to apply, you just have to apply to all the qubits, but you have to go into you have to do it in a Hadamard sandwich. Now, the cool part will be what will happen when we put two logical qubits together, because it's gonna, for example, a control X would kind of be the same, but with like 18 qubits, and so in one you would have like a Hadamard sandwich with controls, and then then you would have one this bit controls the same bit on the other register. Maybe that would be an interesting experiment next time. But this is just for single qubit gates. Okay, so this is just for single qubit gates. How to clean that up? So I'm thinking, basically could just put all that into a class and then have a function that it gives an operation, and it just Hadamard sandwiches that single qubit operation, and then it measures that, right? So you could have a how to make a class? How to make a class in Python? How to make a class in Python? Python classes in Python 3. How to make a class in Python 3? So you define. Okay, this is this scope test. A class. Okay, class. My class. You got attributes, you got functions, and then you can instantiate like these. So we can do something like type that all. So this is going to be a logical qubit, and so we're going to have basically the E circuit is the encoding circuit. That's what we have. Okay, so that should maybe go into the initialization, right? So we're going to have the encoding the E circuit, which is basically a circuit. We're going to have the decoding circuit, which is another circuit. And then we're going to have the Hadamard layer, which is basically a layer of Hadamards on qubits X. What is the for X in range? Okay, yeah. For X in range 9. And so we're gonna what is the calling is not as an anti-object, so this is the initialization thing here. So we're gonna initialize this guy and say basically that's also a circuit. And so we're gonna say basically H layer append this thing, and then we're gonna say basically is where the decoding circuit is here. So we're gonna do decoding circuit, please do this thing. So it's gonna be dcirc. So we'll just keep name short. And ecirc. Here we go. Okay, let's just give it a quick test. If I'm really far off, or if this actually works. So this is can I just then, like, I can now just do logical qubit, right? And then do print LQ circ, print LQ H layer, and print LQ B circ. Does this work? Circuit is not defined. No, sorry. It's circ. Circuit. 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 LQ. Logical qubit. Correct. H layer is not defined. H layer is here. H layer is here. What is it not defined? Okay, so the self, exactly. It's probably the self, and self. Has no dimension. Generator object has attribute, no dimension. What? Append. It's a circuit, right? Circuit. Append. Maybe I kind of mass initialize these in here, and I cannot initialize it here. What does this say? No, I can initialize it here. So, okay. Should I Spread center dimension. What does it mean? TensorFlow generated object has no attribute dimension. Should I inherit from something? Or what? Coding circuit. Oh, that's. I mean, this is eCirc. Okay, but it's not. Doesn't matter. That's not a problem. Problem is in logical qubit. Isn't this H or what? Row types, gate operation. Qubits, cube shape has no. Oh, wait a second. Qubits. Where is qubits? Qubits. Well. Qubits. Oh, but it's still not working. I need qubits. But and now the problem is the same, right? Okay. I'll basically, but I'm trying to clean that up, so I'll just stop the video here for now. I'll try to figure this out in the next video, but that's yeah, because I'm running out of time now. But basically, that's the idea. So we're gonna make a class logical qubit that we can initialize and then just apply operations on top. And we won't do this really fancy, just to encapsulate all that. And it's gonna have a like a sort of a function where you give it a circuit, and then we're gonna sandwich Hadamard the circuit, and yeah, and then we can run it. And then we'll simulate some. Maybe it's just. I think making it a class is definitely. It's totally unneeded. So I don't think I'm gonna go this way. So maybe you'll just like get rid of these and then get rid of the selves and all this kind of stuff. So we'll just keep it. We'll just keep it like. Yeah, we'll just keep it like it is, I guess. Because I would make it a class. I would just make it an actual extension from Circ or something. That would be more interesting. So let's first try it without that added complexity, because I'm a total noob. And so if I do these, basically, and I now kind of, what if I do these, and I basically now say print eCirc, print eCirc, print H layer. Why is it not working? Oh, I'm so stupid. I'm so stupid. I'm so stupid. Okay. So the whole thing with the class was okay. Okay, then let's go ahead with the class. How could I end? Edit. Can I just... I guess I can undo, right? I can undo until I get the whole thing back. get the cubics. Now this was not working, but the reason it was not working is because I had this parenthesis here on. Okay, cool. Yeah, nice, it works. Okay, cool. I'll leave it here. We'll keep building up this class. We'll see if eventually we can play with some, because that's not going to be any extension or anything, or it's not going to inherit from anything from Circ or whatever. Just it's just for playing purposes, okay? So I'm just gonna make that logical qubit class, and we're just gonna. It's actually not a logical qubit; it's really a logical circuit, right? Yeah, I think maybe just again doesn't make sense to have the whole class thing in here. Logical. It's not a logical. It's the Shor. It's a Shor shield. It's a Shor shield. Okay. It's a Shor shield. I like it. SH. No. SSH. No. SS. No. S shield. S shield. S shield. S shield. S shield. Cool. Perfect. Then I think we got it. Really, I think we got it. Because then, yeah. What we're gonna have is we're gonna have basically a function that's gonna be called probably shield circuit. And it's gonna take a circuit as an input, and it's gonna basically what is it gonna do? So we want these to shield the circuit, okay, and then but then we want to run it. We want this shield to actually help us run the circuit. So you know what I mean? So we will shield it, and what else do we want to have in there? I guess we want to also read out the results and output the results, right? So we'll also have a is it to do, and we'll also have a circuit, and so we will also have a def run. It's rather going to be, this is going to be the only public method, really. This is going to be private. If such a notion exists in, so it will kind of return, the results, but we'll see, okay? We'll see. So, and then this is going to call these, and then this is going to do all the encoding, which is basically, probably it's as simple as actually ecirc plus h layer plus the circuit plus another h layer plus the decode circ. And I think this is it, to be honest. I think we're done with this function. That's what it's doing, I think. That kind of prepares the shielded circuit. And then we'll have to figure out how to read. Okay, but that's for 1 qubit, okay? That's here it's not that straightforward. That's just 1 qubit. Assuming 1 qubit. So for multi-qubit, then we need to play with different things in here because it's not that straight. So once we have multiple qubit operations, that's going to be this. We're going to have to split those apart, right, and then connect them somehow. So it's not going to be that straight. Okay, cool, but I like it. That is good.